quick synopsis of what we've seen. The wedge, which can be described in polar coordinates as 0 less than or equal to theta less than or equal to pi over 2, the angle from 0 to pi over 2, r going from 0 to 3. Also representable in x and y coordinates in terms of the equation of a circle, essentially. And the function f of xy equal 1 over the square root of x squared plus y squared, which can be represented in polar coordinates as 1 over 1 plus r. The function integrated over the region can be interpreted as a mass integral if the function is regarded to be a density function, as a volume integral if the function is regarded to be an altitude, and can be subject to a variety of other interpretations. We perform the integral in polar coordinates. We're not going to do the integral in rectangular coordinates. We've already done a number of these, and the same procedures would apply. But in polar coordinates, we simply partition our theta interval, we partition our r interval. We get a partition, we consider a typical increment within the partition, we find the area of that increment, and we multiply the value of the function evaluated at a sample point within the increment by the area of the increment. Our integral is obtained by simply summing up the contributions of f times area, function times area, for the various increments, and taking a limit as our delta theta and delta r distances go down to 0, obtaining an integral, which written in simplified form is this. The limits in the integral are the limits of r with our partition, the limits of the interval that we partitioned. That is the limits of our r interval, which was partitioned to create this entire model, and the limits of our theta integral, our theta interval. Having obtained the expression for the integral, we make some estimates. One estimate is made based on values of f at various distances from the origin, graph of f of r versus r, and estimates that tell us that the average value of this function on this wedge is going to be somewhat less than 1/2. Another estimate in terms of the volume of the three-dimensional graph of f of xy versus x. So this is a graph on this region of, in this case, f of r theta. C equals f of r theta. Versus r and theta. And our estimate of the average altitude of this region was somewhat less than 1/2. Multiplying that by the base area, 9 pi over 4, we obtained an estimate perhaps around 2.3, and not having a whole lot of confidence in that estimate, we concluded that our integral is expected to lie somewhere between 2 and 3. Having estimated and given at least a couple of possible interpretations, we proceeded to perform the integral. First, integrating our 1 over 1 plus r times r dr. Using a straightforward substitution, we obtained the result 3 minus natural log of 4 for the definite integral. Integrating with respect to theta was straightforward. We ended up integrating the integral, the r integral, the definite r integral, came out with no theta dependence. It's just a constant. The integral from 0 to pi over 2 of d theta is pi over 2, so our result is pi over 2 times 3 minus the natural log of 4. That being our integral. I made some estimates, and I estimated this would probably be something around 2.3. When I went to the machine and actually calculated the natural log of 4, which isn't all that easy to estimate. It came out that I was a little bit off. It was 2.53, but that result is clearly in keeping with our estimates.